There are two word problems here, both rational function word problems, and I didn't copy down the graphs because we didn't necessarily need it, but they may or may not give you the graph, and that's okay. We learned other things about the graph already. All right, so this first one, we have n of t, so some function. The n of t stands for the body concentration in parts per million. So some certain dosage of medication is given, and then t hours elapse, and this function models how much is still in your body, parts per million, right? And there are often restrictions because maybe in certain parts, right, the model doesn't fit. So this problem says t must be greater or equal to 15. So this model works for 15 hours or later after given this dosage, right? So that's common in some dosages. Like if you originally get whatever it is injected or however, right, your body may have way up here, and maybe it stays for an hour or two and then it starts to wean off. Maybe it weans off linearly, I don't really know, but at some point, this, whatever this graph looks like, it starts to level out as time continues. All right, so we only care about when 15 hours or more has elapsed. So the part one, it's saying what is the horizontal asymptote? All right, so the horizontal asymptote, remember you are comparing the degrees of the numerator and denominator. Here they're the same, they're both a degree of 1, both t to the 1 power. And if that's true, then you take the coefficients of those variables. So you take 0.8 divided by 5, and 5 goes into 0.8, 0.16, right? Yeah. Okay, 0.16. So the horizontal asymptote is 0.16. So 0.16 parts per million, I'm just going to say ppm, of whatever dosage. Okay, that is how much is still in your body. So therefore, if we were to graph this thing, it never really hits 0, right? It's slightly above. I mean, if this is 1, 0.16 is way down here. It's barely greater than 0, right? A little more than a tenth. So oftentimes, though, they will write it like this: n of t approaches what as t approaches infinity. And this is a pre-calculus slash intro to calculus concept called a limit. As t approaches infinity, this concentration will approach 0.16 parts per million. What does that mean? It means, right, like there will always be a trace of this dosage in your system. It never fully exits, according to this model. Whether it's true or not, I don't know. But according to this model, you'll always have a trace, right? A slight, 0.16 parts per million is nothing, but still something in your system. Okay. So your body will always contain something like this. A small trace of that medication. Something like that. Or indefinitely, I don't know. You get the point. All right, the next example. I have this model, and P of t represents populations in thousands after some time t, which are called months, after property taxes were raised. Okay, so we have some property taxes, they raise them, and this will describe the population to this town or whatever that word problem was. First, they asked for a few values, and I just computed those off to the side before I even made the video. So p of 0 at time 0 is 0. That's kind of weird, right? And this could be what we call model breakdown. A 0 may, this model here might work perfect for all values that we actually like are tangible, I guess, but at time 0, property taxes weren't raised yet, right? So I don't know if this is a just brand new town, new development, and time 0 there wasn't even anybody there yet, and then they had to apply property taxes once the houses were built, right? Like, I don't know enough information about this, but I would assume that this model just doesn't work at time 0, and that's okay. In that case, they should put a time restriction here, like time is greater than 0, because 0 doesn't make sense, but it works for any other month. All right. So first month goes by after property taxes were raised. We have 45, and it's in thousands, and I just rounded. I know there's some other decimals, but about 45,000, 45K. In month 3, so when T is 3, we have about 55K. So property taxes were raised. The population is still going up, right, at that time. But then notice that month 8, maybe it took them some time to sell. Maybe people had bought before they were raised and they were moving in, right? I don't really know. But by month 8, people were, oops, I drew that arrow definitely the wrong way. People were on their way out of here. Okay, they were not happy with the property taxes. Must have been raised quite a bit for, what, 26,000. I mean, almost half the population left from month 3 to month 8. All right, so there's our T-chart. There's some table of values there. Only a select few. The horizontal asymptote, since the degree of the denominator is larger, right? That means the denominator grows extremely large. This is going to be smaller in comparison. If I take a small number divided by an extremely large number, that tends to 0. So the horizontal asymptote is y equals 0. So as time moves forward, this is going to be a ghost town, right? The population is tending to 0 as time goes to infinity. Put that in your own words, however you would say it, but again, as time progresses, people weren't happy. I would assume at some point they're like, hey, we got to do something about this, and they lower them or offer incentives. Who knows, right? Or some people maybe really just don't mind the taxes at all, and they like the low population. Who knows? But in this model, as time moves forward, there will be nobody left in this town.